Okay, good morning everybody, and welcome to this session about space transportation. So I'm Thomas Panozzo, and I will walk you through this presentation, which is roughly about 2 hours, and it will drive you through the different steps, and it's about space transportation. So as we're going to see in the summary, first of all, I'm going to give you a brief description of the European launch vehicles. So the different way that Europe has to get to space. Then I want to walk you through the mission analysis process. So we're going from theory up to the reality. So we see how you really do the things. And then at the end of the presentation, we're going to get through some pictures and video from actual real launch campaign in French Guiana, where all the European launchers are launched to space. So I'll try to be as clear as possible, and let's go. So let's get through the trajectory optimization process, so that we can really understand what it means to optimize a trajectory. Like any other optimization process, you need to have an initial state, a final state, an optimization criteria, and then you need to have an output. So the initial state is basically the position and velocity of the launcher at the end of the atmospheric phase. This is why, because it's not the launcher or the launch pad, because what we do is that during the atmospheric phase, basically the path is imposed, because you need to go to zero incidence until the end of the atmospheric phase. When you are at the end of the atmospheric phase, that is the initial state of your real optimization phase, and the final state is the position and velocity of the satellite satisfying the equation of the aimed orbital injection. So when there is the shut-off of the engine, you need to go in GTO. This is what you want, because in GTO you know that after a few hours you're going to be at geo altitude, and then you're going to get to the apogee burn. Okay? The optimization is the flight time for a given mass, or, and this is what happens most of the time, they use full mass for a given flight time. The flight time is really easy to calculate, because once you know the consumption of your engine and you know how much propellant you have on board, well, you quickly know when you're going to get out, when you don't have any more propellant on board and when your engine are going to shut down. So this is your flight time. And what you want to have is having available that flight time, how much mass you can reach into the desired orbit. This is the real optimization issue, okay? So the output is the thrust vector control, TVC, function of time, so the nozzle orientation, in order to allow the launcher to follow the trajectory that will bring you to this orbit. And obviously the position and velocity of the launcher at each time, which means the trajectory of the launcher. So this is what comes out from the optimization process. Ariane 5, we use the mathematical method behind the optimization is what we call the Pontriagin optimization. And as we'll see later, it's really a state problem, as we'll see later. But before going that, I would like to really make you understand visually about the constraint of the trajectory. So as I was saying, when you take off from the launch pad, it's not because you are in free air that you can go wherever you want. There is constraint even when you are in the sky and in the space. And these lights, which has speed on the horizontal axis and altitude on the vertical axis, just clarify this point, because I was talking about aerothermal flux and dynamic pressure constraints. So there is all a part of the graph that is a no-fly zone for the launcher, okay? Which is the lower part. That part means that you are very low altitude, but very quick, okay? And you don't want to go there, because it means that if you go there, the aerodynamic force, which is, proportional to the dynamic pressure, are going to be too high for the launcher, causing a structural issue, okay? So you want to fly quickly enough and gonna go high in altitude to avoid to have high pressure when your launcher start going very quick. At the same time, you want to avoid the aerothermal flux, which is the second curve, which is not like it go with the cube of the velocity, it doesn't go with the square like the dynamic pressure. This is why the second curve is different. So you want to test being away from those zones. At the same time, you have a verticality limit. So you cannot go straight vertical because if there is any issue concerning the launcher, the debris will fall down on the launch pad and on the populated areas. So as soon as possible, you want to get out from the launch pad and go over the sea. So if there is a problem, at least the launcher fall on the sea. So there is a very narrow path that your trajectory can go through, respecting on one side the dynamic pressure and aerothermal flux, and on the other side the verticality issue, okay? And when you go through, then what you want to do is that you want to get rid of your fairing, because the fairing is 2 tons, so you don't want to bring it with you for a long time. You want to get rid of it as soon as possible. But to get rid of it, you need to get out of the atmosphere, out of the vibration, out of the temperature issues. So you need to go as quick as possible out of the atmosphere, which here we put standard, I would say, at 100 kilometers, okay? So once you get through the very first 2 constraints, your trajectory will change and you are going to go above the fairing release altitude as soon as possible, okay? And once you are up there, well, you can release the fairing and you can shape the trajectory following the Pontriagin optimization method, as I told you before. So if we go to the next slide, there is another constraint that we have to take into account, is the visibility. As it's said very, very clear in the upper part of the slide, you know, you have 2 stations, for example. So the first with the orange view, so the station can see that arc, and then there is a second station placed on the ground track of the launcher, which take another part of the trajectory. What you want to avoid is situation number 1, in which your trajectory, there is a part of your trajectory which is not visible, not by the first station nor by the second one. So in this case, there's going to be a blackout in the trajectory in which you don't know where the launcher is and you don't know what he's doing, okay? So you don't want to do that. You want to do from the first case to number 2, in which you see that the trajectory is a little bit higher with respect to the first case, but in that case there is what we call intervisibility. So that part of trajectory is seen not by 1 station but by 2 stations, and that is the time in which you pass the telemetry from 1 station to the other, is when you have this intervisibility. So this is another constraint that makes you understand that you can shape the trajectory. You need to be very attentive how you shape it, because if you don't shape it properly, you can miss some constraint, which are, for example, this one, the visibility one, is very, very important, okay? On the lower part of the slides, you can see actually what the ground track of the Ariane 5 launch to the east, so to GTO orbit. So the launch pad is Kourou, and then what you have the Natal ground station, the Ascension ground station, which is a little island in the middle of the Atlantic Ocean. You have Libreville, which is in Gabon, and you have Malindi in Kenya, okay? And these 5 stations, with their own mask, so with their own visibility field, they are able to track Ariane 5 from launch to insertion in GTO orbit, okay? And this is just an example of how you can get visibility for Ariane 5. Another interesting point is how you can get onboard guidance, because everybody is asking me, how can a launcher be completely automatic? Well, the onboard guidance is done in the following way. There are some measurements which are provided by the inertial platform. So if you remember, I said that in the VEB, the vehicle equipment bay of the launcher, there are some measurement unit, okay? So gyroscope and accelerometers. So what happens is that this inertial platform, they measure the angular position of the launcher in an inertial space. So it's like an artificial horizon for the airplane is the same thing. It works in the same way. So you set the reference frame, and then whatever is the position of the launcher with this reference frame, the instrument gives you this angle, okay? So this is called gyroscope, okay? At the same time, you can get acceleration from the onboard accelerometers, which are put in such a way that you have the acceleration on the 3 axes, on 3 perpendicular direction, okay? So these are the measures that you have on board. So what happens is that the 2 onboard computer, from the angular position, so they can derive the angular velocity, simple by derivation in time, and they can have, if you have the linear acceleration with the accelerometers, you can integrate in time and you get the velocities and the position, okay? So with this information, you know where you are and what is going to be your attitude, so your angles, okay? And basically, this is all the brains of the launcher, because through the information given by this inertial measurement unit, the launcher knows exactly where it is and where it has to go, because it's doing this optimization process at 72 Hertz. So once every X seconds, it performs the loop and know exactly where it's going by applying these rules, okay? And what we can go to the second slide is to give you an example of this famous Pont-Trier gene optimization process is done. You have point A, point B, you have constraint, which is here like an obstacle, and the optimization tell you whether it's better to go around the problem, to go over it, you know. And the optimal trajectory is the one optimize one criteria and satisfying all the constraints. So the constraint we have seen, the constraint over thermal flux, dynamic pressure, to be able to the vertical limit and the fairing. And then what you do, you apply this process in which you say that is a state problem. So the state is R and velocity. So 6 elements, R is the position, V in the velocity, in the vectorial form, so 6 elements. And you say that the derivatives in time of the state is the velocity, and then the evolution of the velocity follow the Newton law. mv dot is equal to the sum of all different force, which is gravity, propulsion, aerodynamic force. Okay, so state vector, 6 elements. U is the thrust direction function of time, and the different parameters to be taken into account are the typical launcher parameters like the mass, combustion time, and launch azimuth. Again, here is a little bit of repetition of what is the trajectory mains constraint. Safeguard of humans, stage re-entry, structural and thermal efforts, aerothermal flux on upper stage with after fairing jettisoning, and launcher visibility from ground station. Okay, so if we apply all of these to Ariane 5, this is what we get. We get a typical Ariane 5 GTO mission profile in which we see the launch pad, first atmospheric flight, at the end of the atmospheric flight, separation of the booster, okay, roughly about 140 seconds. After 200 seconds, this is the fairing release, so it means that we are above 100 kilometers of altitude. After 8 minutes, the main cryogenic stage has consumed all of its propellant, so it's a dead body and you want to separate of it. So this is picture number 4. Why the mission keep on going? Well, the EPC basically fall down, and there is a maneuver that we call tumbling, in which we open a draining valve of the tanks, and with the pressure of the tanks, this draining valve, which is placed in a very special part of the launcher, make the EPC to tumble while it's re-entering. So if you just imagine this cylindric part re-entering into the Atlantic Ocean, what you want to avoid is that there are aerodynamic force that can deviate the trajectory in one side or another. So by make it tumbling and rolling like this, what you are able to do is you are able to reduce the footprint of the impact in the sea. Because just keep in mind that every time there is one of these stage fall down on the sea, you have to issue a NOTAM. So a NOTAM is a notice to airmen, which is available for planes and ships, and tell you not to be in a certain place from this time to this time. So every time there is a launch, what happens is that there is the French Space Agency which notify to all the ship, to a appropriate entity, I would say, to deliver the message and not to go through a certain footprint, a certain area in the ground or in the air between this and this time. Normally this is not a problem because it's very, very short time. It's probably around 10 minutes, 15 minutes, and the area on the ground is few hundred kilometers, just to cover 99.999% of the cases. And so far no incident have occurred, so it's very, very well managed. Okay? What happens at the takeoff is that you know that the difference between liquid engine and a solid propellant engine is that a solid propellant engine, you cannot shut it down. Okay? Once it's switched on, it goes until the propellant is over. The liquid engine, whether it's going to be cryogenic or storable propellant, you can shut it off because you just need to close the valve that feed the combustion chamber and the engine stop working. So what we want to do, what we do on Ariane 5 is that at the very beginning we switch on the Vulcan 2 engine, which is the cryogenic one, and we test it for 7 seconds. What means? What means that after transitory, we want to test that the engine is ready for flight because we don't want to take off with a failing engine. So we switch it on, okay, and for 7 seconds, the onboard computer monitors the data of the engine. So the turbine speed, the combustion chamber pressure, and all the main data to be sure that when the strap-on booster switch on, well, you're done. I mean, you're taking off when the strap-on booster switch on. So you want to be sure that the Vulcan engine is working properly. And so what happens is that during these 7 seconds, if there is any of these parameters out of the specification or out of the range, well, the OBC shut down the engine without switching on the booster, okay? That's what we call aborted mission. And this is, I would say, this is a very smart move because you don't want to go to fly with an engine which is not performing because the risk is that you lose the mission. So it's better to have an aborted mission on ground in which you can fix the problem rather than go on flight with an engine which is not performing as supposed. Okay? So from switch on, you switch on the Vulcan 2 and then you switch on the booster, so you have the takeoff. What happens after 2 minutes, as I said, the booster consumes all the propellant, and there is an accelerometer on board that measures the thrust of the booster. And when this accelerometer see that the thrust is going down, which means the booster have stopped giving thrust and they are becoming a dead weight. Well, before they becoming a dead weight, the accelerometer triggers the separation of the booster. So the booster are separated, and so they are used only for the time in which they give you thrust. They give you, really force to take out from the pad, but after it they are separated, okay? The main stage shutdown occurs when the intermediate target orbit is reached. So the separation between main core and the last stage occurs 6 seconds after the shutdown, okay? After this separation, as I was saying, the main stage is put in what we call a flat spin mode by opening a lateral venting hole in the hydrogen tank. And this control procedure provides actually a re-entry and splashdown in the Atlantic Ocean with a reduced footprints, okay? The upper stage ignites after a few seconds after the separation from the main stage, and then basically for 9 minutes you will be able to bring the satellite into final GTO orbit. So when you are into orbit, what happens is that as soon as the onboard computer realizes the launcher is on GTO orbit, there is a shutdown on the engine. So the valves are closed and the engine do the shutdown. So now you are in what we call the ballistic phase. So no more thrust on the launcher and you are on GTO orbit. At that point, the upper stage of the launcher with the satellite they perform three-axis maneuver around the three axis, which is roll, yaw, and pitch, in order to separate the satellite during the appropriate separation direction, because all the satellites are different. All the satellites have specific thermal, sun constraint, so they have separation direction which are very, very specific. And so Ariane 5 last stage, through altitude control thruster, he can orientate on different directions depending what are the needs of the launcher. Then they can be slow spin separated, high spin separated, or three-axis stabilized, depending on what is the need of the customer. This table is like a resume of what we have just said so far. So ascent phase, attitude load, and trajectory constraint. And it is very, very nice scheme because it tells you basically all the information are here. And they tell you depending on which part of the flight, so EAP, which is the solid propellant rocket booster flight, EPC flight, and upper stage flight, what are the attitude loads used, and what are the trajectory constraints that we have to take into account for the mission. But it's all stuff that we have seen. Here is just some nice graph that tell you the trajectory profile, and they describe a little bit what are the value and the trends of the different Ariane 5 mission profile. In the first, you can see there is relative velocity versus time, so this is easy to understand. Time is on the horizontal axis and relative velocity on the vertical axis, and you see very, very well the three parts of the launcher, so solid rocket booster phase, main cryogenic core phase, and upper stage, okay? And obviously, all of the velocity is increasing all the time, okay? And at the end of the launcher trajectory, you reach 9,200 meters per second velocity, which is the velocity required in GTO transfer orbit. The altitude is on the right graph, and it tells you that there is a very first part in which we get out from the atmosphere as quick as possible for the fairing constraint, which I just told you. Then there is a flat part in which you basically focus on augmenting and increasing your velocity rather than your altitude. So you stay at constant altitude and you increase your velocity, and then you increase your altitude to go to GTO. And at the end of the launcher thrust phase, if you see to the graph, you are about 550 kilometers high, and after about 1,500 seconds of thrust. In terms of acceleration, so this is what we call longitudinal acceleration. So is the acceleration along the axis of the launcher, the vertical axis. So it is the acceleration possibly felt by a person which is sitting with the back looking the floor, okay? So in a vertical position like this. And so you can see that during the EAP phase, so before the moment that we call H1, just before the solid rocket booster separation, we get an acceleration of roughly 41 meter per square second, which is roughly about 4 Gs, just before EAP separation. Then during the main cryogenic core flight, the acceleration is smoother, still arrive at probably 3G at the end of the EPC flight. And what you can easily understand is that the acceleration is increasing because the thrust of the launcher is the same, but since the launcher is consuming propellant, the mass of the launcher decreases. And since acceleration is equal force divided by mass, if the force is the same but mass decreases, the acceleration is increasing. This is why the curve is like this, okay? And also for the last stage, you see is exactly the same. It's not so quick like the second stage because the consumption of propellant is much lower, but still is in increasing trend. These two graphs just give you an idea of what is the evolution of the mass of the launcher. So as I said, on the launch pad, the launcher is about 800 tons, okay? And after the separation of the booster, it goes down to exactly 250. Because, as I said, the booster consumes so much propellant that after 2 minutes, the launcher is weighing 1/3 of its takeoff mass, okay? So this is the mass, the thrust we have already discussed by the launcher. Just If you see the different thrust level of the launcher, the first part is the solid rocket booster, and you have a thrust of 1,002,000 kilonewton, which is 1,200 tons of thrust at the beginning. When the booster is separated, you go down to 135 tons thrust, which is the thrust of the Vulcan 2 engine, and then you go down to 65 kilonewton, which is the thrust of the upper stage. So the more you move in time, the less thrust is of the launcher. This is about the visibility issue, as I already told you. So what happens lately is that we took into consideration the fact that we can lose some telemetry, and we can live with the fact that during some very steady phase, when there is nothing happening, we can basically store some of the telemetry on a onboard mass memory, and as soon as we become visible the next station, we can release all the telemetry bits and to the next station. So as of today, since now Ariane 5 has more than 55 launch and is working very well, we are ready to release the constraint that I described at the very beginning of the lesson, to have the full visibility along the trajectory. And in this moment, we can basically allow to have a 70 seconds gap between Natal and Ascension Island, okay? Knowing that in any case, we will get the telemetry from these 70 seconds as soon as we become in visibility of the next ground station. I would say in ground station coverage, this gives you an idea of what is the elevation. So just to give you an idea, is the angle between the horizon and the direction of visibility of the satellite, of the launcher, sorry. So basically when you have a ground station which is placed in Ascension Island, okay, in the middle of the Atlantic Ocean, what you're gonna see is the launcher is gonna come up from the horizon, okay, because the Earth is spherical. So at the beginning you're gonna see the launcher come up from the horizon. You're gonna track it, so the launcher can be in front of you, can be over you, or can be behind you, okay? And the angle between the horizon and the direction of the launcher, that is called elevation. So for example, there are some ground stations like Malindi, if you see, is the violet line in which the launcher comes up from the horizon, but basically it's really, really going over you, like vertical. So the elevation is almost 90 degrees. So the antenna has to follow the launcher 90 degrees and going down. There are other ground stations, like for example Natal and Ascension, in which the launcher, because of the trajectory, is seen at very, very low elevation, like 10 or 20 degrees maximum. So you see, for example, Natal and Ascension, the launcher is seen at 5 degrees. It means that the dish of the ground station is basically horizontal with respect to the ground. What I propose to you here is a flight sequence. I'm not going to get through all these numbers because they are quite boring. What I would really you to put your attention is try to put like time and velocity and altitude of the launcher and see how quick the launcher gets velocity and altitude during the mission, okay? And next to it there is the visibility from which stations, from the the green bar tells you which station is able to track the launcher depending on all the different phases. And you have different events, you have the ERP ignition, the lift-off, the end of the vertical rise, you remember the verticality constraint I was talking to you about, and the beginning of the pitch motion, and then you have Mach 1, so the first you reach sound velocity, maximum dynamic pressure, maximum longitudinal acceleration, ERP jettisoning, and you have all different kind of events that you can place exactly at any given time. So this is the idea.